All right, let's talk about one of programming's most elegant and, sometimes most dangerous concepts, recursion. By the end of this, you're not just going to know what it is, you'll get when to use it, and maybe even more importantly, when to run in the other direction. So what is it, really? At its heart, recursion is just a function that calls itself. Think of it like a set of Russian nesting dolls. To solve a big problem, the function kind of opens itself up to reveal a smaller, identical version of the same problem, and that one does the same, and so on until you get to that tiny little doll at the center that can't be opened anymore. So here's the game plan for today. We're going to start with the core logic, see how beautiful it can be with a simple example called factorial, then uncover a pretty serious performance trap with a Fibonacci sequence. And don't worry, we'll finish up by looking at the powerful ways you can tame it. Okay, let's dive right in. For recursion to work and not, blow up in your face, every single recursive function has to follow two strict, non-negotiable rules. If you get these right, it's elegant. But if you get them wrong, well, you get chaos. First, you absolutely, positively need a base case. This is your stop sign. It's the emergency brake. It's the condition that tells the function, okay, that's enough. We're done here. No more calls. And second, you've got the recursive case. Now this is the engine. It's the part that says, do it again. But, and this is key, always on a slightly smaller piece of the problem. So you're always getting closer to hitting that base case. Which, of course, brings up a really important question. What happens if you forget that stop sign? Right? What if you're so focused on the do it again part that you forget to build an exit? What happens when a function just keeps calling itself? Forever. You get a crash. See, every time a function gets called, it uses a little bit of memory in a place we call the call stack. Without a base case to stop the loop, the calls just keep piling up and up and up until the program literally runs out of memory and just gives up. And that, my friends, is the classic, infamous error known as a stack overflow. Okay, now that we know the rules and the risks, let's see recursion in action with a perfect use case where its beauty really, really shines. Calculating a factorial. Just look at that code on the left. It's so clean, right? It perfectly mirrors the actual mathematical definition. And on the right, you can see how it works. Factorial of 4 has to wait for the answer from factorial of 3, which waits on factorial of 2, and so on until it hits our base case. Then, the answers start to cascade back up the chain, multiplying as they go until we get our final result. This is a perfect example of just how elegant recursion can be. Now, that seemed pretty simple and powerful, didn't it? But this is exactly where that double-edged sword thing comes into play. Let's move on to another famous sequence, Fibonacci, to see how this beautiful tool can turn into a total performance nightmare. Now, the code for a recursive Fibonacci looks just as simple as the factorial one, but what's happening behind the scenes is a disaster. I mean, just look at this call tree for calculating a tiny number like the 5th Fibonacci number. Do you see all those repeated calls? We are calculating the exact same values over and over and over again. It is incredibly wasteful. And this isn't just a little bit inefficient. It's exponentially slow. As our input number grows, the number of operations just explodes. A normal loop-based solution grows in a straight, predictable line. But our recursive function? It shoots up into the sky, making it completely useless for anything but the smallest numbers. So does this mean recursion is just broken for problems like Fibonacci? Not at all. We just need to be a little smarter. We've got two main ways to fix this mess. We can use a straightforward loop, which is called iteration, or we can use a really clever trick called memoization to make our recursion way more efficient. And this table here, this really lays out the trade-offs. You've got your naive recursion, which is super easy to read, but the performance is just awful. Then you have iteration using a loop. It's fast, it's efficient with memory, but sometimes the code isn't as clean. And then there's memoization. You can think of it as smart recursion, which tries to give us the best of both worlds. Memoization is such a cool technique, and it's based on a really simple idea. If you've already done the hard work to figure something out, just write it down. The function keeps a little cache, a memory of previous results, so before it does any work, it asks, hey, have I solved this one before? If the answer is yes, it just grabs the stored answer and avoids all of those wasteful, repeated calculations we saw earlier. It's so simple, but so powerful. So what's the bottom line here? The big takeaway is that recursion isn't just good or bad. It's a specialized tool in your programming toolbox. And the real key is knowing exactly when to pull it out. You should be reaching for recursion when the problem you're solving is itself recursive. Things like navigating a file system, or processing data in a tree, or certain divide and conquer algorithms. These are perfect for recursion. In those cases, the recursive code is often way clearer and more elegant than trying to force it into a loop.
This quote from our source material just sums it up perfectly. You have an elegant, natural tool that can be costly. You have a workhorse tool that's super efficient, and you have a smart tool that tries to blend that elegance with much better performance.
And that really leaves us with the final thought you should take away. Understanding these trade-offs between clean code, raw speed, and memory, that's what separates a good programmer from a great one. The real skill isn't just knowing how to write recursive code, it's knowing when. The choice is always yours.